Right, grade 12 University Prep Physics. This is Ampere's law. This is mighty confusing stuff. When you first learn it, I'll give you a little bit of a relief that it translates into just an easy formula. Okay, so from anything we need to worry about in high school physics, it's just a formula, but the concept of it is pretty hard to understand. Ampere is Andre Ampere, and this is the result of studies measuring magnetic field strength and collecting data. So he didn't kind of theoretically come up with this law, and this is the law right here. He didn't theoretically come up with that. He measured it, and he measured like tons and tons of data and came up with this relationship. And we'll talk about what it means, and then we'll make it something that, as I say down here, how can we make this something practical? Because of course, I don't think you can use that equation very easily. Okay, so the goal is to be able to look at a conductor. Okay, so a conductor is carrying electrons through it, and somewhere near that conductor or on that conductor, you want to measure the magnetic field strength. Okay, and that's the magnetic field strength that's caused by that electric field. Remember that every electric field causes a magnetic field. So if you want to measure that field, then this is how you do it. This is where we're going. And so what his data showed, okay, his data showed that any closed path, now you see right here I drew a circle, but the closed path could be amoeba shaped. It could be shaped like anything, okay, as long as it's a closed path. And let's just go through I'll try to relate sort of the words to the equation here. Not actually an equation, is it? There's no equal sign, but to the relationship. It says the sum of the products. Okay, first of all, sum, this symbol, if you've taken data management, you know this. That's the symbol for the sum. So it's like if you added them all up, it's sum of the products, and the product is B times delta L. So that's the product, those two things multiplied together. So of the scalar component of the magnetic field strength, parallel, that little sign means parallel, to the path segment. So just jumping to the picture, okay? So here in this case, I'm looking at a circle, and there's electron current flowing through this circle. And I want to know right here, this is the idea of if I knew B, the magnetic field strength right here, sort of that's multiplied by sort of a tiny little segment of length, okay? And that's what it means. It means if I found those two, that would be proportional to the current. So if I raised the current, then this product, delta L times B, would be bigger. That's what proportional means. And if I decrease the current, this product would be lower. Okay? So really that's all this is telling me, and we can't use this. This is going to turn into an equation that you'll just be able to use. Okay? So how can we use this for something practical? Well, we're going to take the case that I drew here, but it is actually a unique case. It's the case where the path is a circle, because like I said, it could be amoeba shaped, it could be like the outline of Canada, it could be any shape you want, right? But, we're choosing a circle. So take a unique case where the enclosed path is a circle. Okay, well if you do that, and we just took this part of that relationship, the sum of the lengths, well, if you took the whole thing, it'd be equal to the circumference, so 2 pi r. Okay? So essentially, I'm going to take this with this, the sum of the lengths out. I can take that out of the equation now. Okay? And the second thing I can say is that if you have a circle, sort of everything equidistant from the center, you can say that B is going to be constant at any one point. So if I measured B here, at least the size, the magnitude of B, it would be the same here as here as here as here as here. So that means that B is a constant. So the sum of all the little bits of B would all just add up to B. So that leads us to a new proportionality, which now we can use this, or we're getting close to using it, right? So instead of the sum of delta L, I've got 2 pi r, and I've just got B. And now that's proportional to my current. Okay? So what I'm trying to do here, by the way, I'm just going to jump the screen, okay? I'm trying to find the magnetic field strength B somewhere near a conductor. So I'm going to isolate this equation for B. Get B by itself. And it's still not an equation. I keep calling it an equation. It's still just a relationship, right? I can't use this yet as an equation. So if I want to use, this is Ampere's law though, and if I want to use his law to find the magnetic field strength any distance from a cylindrical conductor. It has to be cylindrical, obviously, because of the idea that it has to be a circle. So this is only true if we're talking about something that's a circle. Okay. However, what Ampere did is, with this relationship, when you have a proportionality, it's like you can make a graph out of it. And if you measured field strength and you measured I, that's an I, not a 1, I over 2 pi r, and you just sort of continually changed r and I, so this number changed for any given situation, kind of like Newton's the universal gravitation constant. You always get the same number. It was always this. Okay, and what a number it is. 4 pi times 10 to the negative 7. The units, you're like, huh? What do those units mean? It just means that if you think about slope as rise over run, well, the rise is Teslas, because that's B, and the run is amps over meters. So when you divide it, it becomes Tesla meter over amp. So you don't need to worry about the units. It's just, it is what it is. But this slope becomes a kind of like another constant that you'll have to, and you're going to be upset when you see the symbol we give it, but it's a constant that you'll put on your formula sheet and you need to know. Oh, there must be more. Yeah, here we go. So this allowed us to come up with the equation, okay? So now we have a real equation. This is the slope. It looks a lot like the coefficient of friction, but in fact, in an electrical application, and it has a little naught beside it. They call it mu naught, not mu zero, mu naught. It is they gave it the name permeability of free space. And you're thinking about, what does that mean? Well, think of it as, the permeability of a magnetic field through free space. Okay, and there's so that's the value of it. And so this number is always true. Right? This needs to go on your formula sheet. Mu naught equals that, 4 pi times 10 to the negative 7. And just some details then for this equation, that's our application of Ampere's law. So when we use Ampere's law, it's always going to be in this form. Okay? Where we're thinking about a circular enclosed area. So I is the current, and I italicized and made it reddish, the inside, because that's important, that's relevant. Okay, the current inside the radius r. And r, by the way, doesn't need to be just the radius of the conductor, but we'll see that in the example. Okay, so just a little example. This one's easy. So it says, at what distance from a straight conductor? And I guess something that's implied, by the way, is it's from the center of that conductor that I'm assuming. It's carrying 2.4 amps. And I want to know at what distance, kind of the R, is the magnetic field this? Is that the B? Okay, so that's the information I have. It's just a straight application of the formula where we're looking for R instead of B. So we know at this particular location, that's the magnetic field strength. We're going to calculate the R, which is to the center of the conductor, not to the surface. We don't know anything about the diameter of the conductor, so. Okay, you just sub in. You can write down all the numbers, but you can just see it's just subbing in the numbers. Mu naught is this beautiful thing. 2.4 amps, 2 pi on the bottom. So just algebraically, by the way, if you look at what I did here, okay, if you divide the 4 pi by 2 pi, then you don't have any pi's in your equation anymore. It just becomes 2 times 10 to the negative 7 times 2.4. This, I think, makes it easier to put in your calculator without screwing it up. Okay, so important to make this step. And then you end up with that number, which, I mean, what's a good number? We don't really know, except for, because field strength, we don't have a good feel for magnetic field strength, except to say that, 9.6 millimeters is a reasonable number when you think about something real like a conductor. You're not talking about kilometers away, right? So it kind of makes sense, about a centimeter from the center. Okay, you might need to pause to write, but I'm going to move on to our second application. Okay, so our second application, this is a very common question, a common test question, a common assignment question, sometimes, but not always, a common exam question. So it's worth, paying close attention to how to do this and some of the details. It's not hard, it's just an application of the formula, but there's some understanding to know. So we have a copper rod, and its radius is 8 centimeters. So what I drew here, by the way, is the center and then 8 centimeters away, of course in meters. The rod carries 2 amps, uniformly distributed across this cross-section. Because, of course, we're assuming that, and that you'll always assume this in grade 12 physics anyway. It's not like it's concentrated in the center or whatever, it's just throughout the rod. So this is a picture of the rod, right? And the 2 amps is going all within it. And we want to find the magnetic field strength sort of right at the center, 4 centimeters away from the center, 8 centimeters away from the center, so on the surface, and then outside the rod, 10 centimeters from the center. Okay? And this one is the toughest. We'll talk about it later. So I kind of should have made it part D, but whatever, I didn't. So we'll actually leave B till last. So first of all, for part A, what is the magnetic field strength right in the middle? It's kind of like, it's very similar to the question is, what is the value of G at the center of the Earth? Kind of the same question. Is it infinite or is it 0? And that's a good question. And it's the, like I say, by the way, oh, I bet you put an E. I've been trying to figure out how to spell mathematicians. Is that it? Anyway, I don't think that's right. Anyway, I can't spell mathematicians. Anyway, so inside a radius of 0, there's no enclosed current. So our I is 0, but also R is 0. So it's the great question. What's 0 over 0? And I don't know the answer. Ask Mr. Restall. Is it infinite or is it 0 or is it undefined? And that's the exact same, by the way, if you were trying to calculate the gravitational field strength at the very center of the Earth. Is it 0 or is it infinite? Because your R is 0. Your R is 0, which is on the bottom. Yeah. So it's 1 over... Oh, so again, is it infinite? I don't know. Anyway. So inside a radius of 8 centimeters, so part C is 8 centimeters, so that's just on the surface here. So this one's actually very straightforward. This will just be, you got the whole 2.0 amps contained in that area. Okay, so your I is 2.0 amps. And you just apply the formula, just as you see it. You know, you'll have to practice put it in your calculator, but you get 5 times 10 to the negative 6. I don't know if that's a reasonable number, so I'm not going to check mark it. When we have something to compare it to, we might. So this is just straight application of the formula, no problem. And actually, same as 10 centimeters. At 10 centimeters, it's still the same thing. You got the whole 2 amps in the inside, but now your R is 0.1 instead of 0.08. So now you've got a slightly smaller number, which this makes sense, right? Now that you have something to compare it to, it makes sense that it's a little bit smaller because it's a little bit further from the center, just like the gravitational field strength is a little bit smaller, further from the center of the Earth than, say, it's not like it's 9.8 right at sea level. Well, if you go to the top of Mount Everest, it's a little bit smaller than that. So that's actually kind of the same. Okay, part B. Now, it's not that part B is that difficult, but here's the thing. Inside a radius of 4 centimeters, the thing you have to figure out is what's I. And your gut's going to say that, well, if I have 2 amps at 8 centimeters, it must be 1 amp, right? But in fact, that's not true because the amount of current flowing inside this radius is proportional to the cross-sectional area, not the radius itself. Okay, so you have to do this process. And just let me remind you, you will see this at some point on some evaluation of some flavor. You have to remember you can't just cut it in half or whatever. You use this relationship where I say my cross-sectional area for 8 centimeters divided by the cross-sectional area for 4 centimeters, this is just a proportionality, right, is equal to the current inside 8 centimeters divided by the current inside 4 centimeters. And you can do all that math, blah, blah, blah. It, in fact, is a quarter of the current. Okay, so then you can start to think, well, can I just figure that out myself then if it was, you know, it's like if you half the radius, you quarter the current, then maybe if you make a third the radius, it'd be a ninth of the current, that sort of thing. Okay, it's a square rule. But if you're not too confident just doing that in your head, just use this equation. Okay, so now you know your current, and now it's just this equation. So R is 0.04, I is 0.5, and you get a number. And then, yeah, I think, you know, putting the question mark on it or putting a check mark on it, it's a little surprising it's not this, you know, you think on the surface there'd be a little bit less, or it'd be less on the surface just because here we're closer to the center, so you'd think that the field strength would be higher. But again, similar to going, burrowing through the earth, when you get to a certain point, if you're right here, you've got gravitational pull pulling you up, like all the mass on this side of you pulling you up, as well as the pull down. So that the field actually drops, right? And that's the same here, right? So there's because magnetic field is a vector, right? It reduces. So it seems surprising, but it's like the outside stuff cancels some of it. Okay, but it's all taken care of in the formula. All right, very good. Okay, I want to quickly jump through. This is quick and easy. Magnetic field strength inside a coil. So say you had a coil, and we set these up in grade 11 quite frequently. If you want to know how strong the magnetic field is, like smack dab right in the middle, and that picture, by the way, is pointing inside, not on the surface, but inside. Here's the formula for it. We don't need to go through how to get it. So it's the number of wraps times the current divided by the length of the thing. Okay? Multiplied by our constant. So write this down on your formula sheet because it's sometimes a multiple choice question. It's pretty easy. There's nothing much I can do to this to make it harder. You'll be given N, given I, given L, or looking for one of those things, right? So just looking at the equation, calculate the magnitude, so the size of the field strength. There's our L, there's our N, there's our I, okay? And you solve for B. Okay, so that's pretty easy. And yep, only one more lesson in this unit after this.